All right. So this particular case, first thing, you were given a pKa. The expectation is that you would turn that into a Ka. So just like if you have a pH and you want to know hydronium, it's 10 to the minus the pH is the hydronium concentration. So therefore the Ka is 10 to the minus pKa. So if you take that, Ka is equal to 10 to the minus 3.15, you get 7.08 times 10 to the minus 4. Okay. Then the other difference is concentration of the acid is different than the concentration of the conjugate base. So this time we do not have equal amounts. So that's going to change the pH. It also modifies your calculation slightly. But it is still true that the final pH, and remember this is my personal check, the final pH is still going to be somewhere near the 3.15 pKa. So maybe up 1 or down 1, so maybe somewhere between a pH of 2 and 4 would be a reasonable value. So in the back of my mind, that's my check. That will actually calculate the concentrations. I know that the pH has to be somewhere between 2 and 4 for a typical buffer, so I'm good. So that's the number I'm expecting it to be. All right. So to actually do the calculation, I'm still going to do everything that I did before. I need an ice diagram. It's still going to be based on the weak acid equilibrium, because the weak acid equilibrium has hydronium in it, and I'm going to take the negative log of that. I cannot simply take the negative log of Ka because I don't have equal amounts. So I can't use that shortcut. So if you want to use that shortcut, that doesn't work here. But still, my ice diagram. 0.14 molar is the initial concentration of my weak acid. 0.071 molar is the initial concentration of my conjugate base. Change is still going to be down a decrease for the weak acid and increase for the conjugate base. If I happen to be wrong, then it would just mean my sign is wrong when I get down to the end. I'll have a negative sign when I'm expecting a plus sign. But wait, if hydronium starts at 0, it can only go up, so I know that has to be plus X. So these have to be the correct signs. At equilibrium, 0.14 minus X, 0.071 plus X, and then of course X for the equilibrium concentration of the hydronium. I know what the equilibrium is going to look like. It's going to look like this, products over reactants. So there's my equilibrium. I need to find the value of Ka from the pKa. So I get 7.08 on 3 significant figures. Since you have 3 significant, times 10 to the minus 4. I plug that in, but wait, let's make our assumption that X is small. Find the value for X. So I solve this. X is not, again, X is not Ka because I don't have equal amounts. But still, the ratios are going to tell me what they are. So in this case, X is 1.4 times 10 to the minus 3. Check my assumption. I'm around 1%. When you're checking your assumption, you got a couple of choices. You can take just the HA concentration. That's what I show here. Or you could take the A minus concentration because they're not the same. Which one do I compare it to? Technically, because this is Ka, I need to compare it to my weak acid concentration. Okay? But if you want to be safe, compare it to the smaller of those two. Still, I'm within 5%. So, I can calculate those other values, but I really don't need those other values. What I want is X, because that's the value of hydronium. Take the negative log of that, and then I will have the pH. 2.85. And that's what I solved for most people. If you want to check, Then you plug all those equilibrium values back in and see if I get the original Ka, 7.2 times 10 to the minus 2. So that's how you solve it. Having said that, as it turns out, there's an error up here. Because if you look at the value for Ka in the back of the book, you don't get 7 times 10 to the minus 4. If you look in the back of the book, it says 3.5 times 10 to the negative 4. Okay? So according to the back of the book, the value is 3.5. I guess what I need to do is go out and see if I can corroborate one value versus the other. But I think that's right. 3.5 times 10 to the minus 4. That's what the back of the book says. Which means that the pKa is not 3.15. The pKa is 3.45, which I would round to 3.46. So, if you went back there and used this value, then it's going to change the value for X. So instead of 1.4 times 10 to the minus 3, you'll have a slightly different value. Change, you'll get a slightly different pH. But this is how you solve the problem, which is exactly what we did for the first part of our time here. Questions? Comments? Henderson-Hasselbalch equation. If you take a look at the 2 ice diagrams that we've used so far, yeah, one of them had equal concentrations, one of them didn't. And then that shortcut that I showed you the other day about what the H concentration is going to look like, and then you know that you take the negative log of the square root of the Ka times the initial concentration, right? In equation form, that is essentially something called the Henderson-Hasselbalch. Calculations of this type are common for buffer systems. To need to know what the pH is based on any particular starting concentration. Because you don't always simply use equal amounts. It really depends on what you want the pH of the buffer to be. And as I said before, I don't have a lot of control over the pH of the buffer, but I have some control. So the Ka of acetic acid causes an equal mixture buffer to be at pH of 4.7. I have no control over that. That comes from the Ka of acetic acid. You may also quickly notice that an equal molar mixture of hydrofluoric and potassium chloride would have a pH of 3.15 in our numbers, or 3.45, whichever one of those is correct. I'll figure that out. Anyway, we know what the pH is going to be for an equal molar mixture. If I change those ratios, I can change the pH, but I can usually only go down by about 1 pH unit or up by about 1 pH. So I have roughly a plus or minus 1 pH latitude when I want to make a buffer. And what the Henderson-Hasselbalch equation does is it tells me for any particular ratio of conjugate acid, conjugate base, based on its own Ka. And Henderson-Hasselbalch uses those values and quickly determines what a pH is. So if I want to use this Henderson-Hasselbalch equation to recalculate the previous, what I need is the pKa, 3.15, in the numbers we were given, you were given, okay? What is this an example from the book? Now, conjugate base anion was 0.071. Weak acid concentration was 0.14. So the Henderson-Hasselbalch equation says, if I take the log of 0.071 divided by 0.14, whatever that value is, if I take the log of that and then I add it to the pKa, I should get my 2.85 that I got all together. Like I said, this is the Henderson-Hasselbalch equation. It's just a quick way of really summarizing what the ice diagram accomplishes for us. Same thing. My conjugate base concentration, my weak acid concentration, and the actual Ka value are all in there, and this is the form of the pKa. So it gives me the same values. It's just a quicker, to me, shorter way to get to that result. If you like ice diagrams, you can continue to use an ice diagram. But if you have a buffer, this only applies to a buffer. Don't try to apply this to a pure weak acid or a pure salt of the conjugate base. Don't try to apply it there because it won't work. It's only for a buffer system. You have both the weak acid and its conjugate base. The weak acid and its conjugate base. Very specific to this Hasselbalch. But quick, simple, short way. And by the way, this equation is based on that x is small approximation. If for any reason the x is small is not correct, this will lead you to the wrong thing. If x is bigger than 5% of the initial concentration, you must use the quadratic. And the Henderson-Hasselbalch derivation is based on x is small. Does not take into account when quadratic has to be used. So just a couple of cautions there, but most of the time, x is small works. We've been using it a lot, and it continues to work very often for us. So that's what the Henderson-Hasselbalch equation is all about. For you math types, you're welcome to work yourself through this. I'm going to go through this quick, but if you're not a math type, hey, just use the Henderson-Hasselbalch equation as it is. That's perfectly acceptable. But there's my equilibrium expression. If I rearrange my equilibrium expression, I get hydronium on one side, and you know the negative log of that is pH, right? So you can see pH beginning to form, and there's a Ka, so pKa is going to start to show itself on the right-hand side. Okay? So if I take the negative log of both sides of those, which means put in a p in front of their values. What logarithms do, remember that if you multiply things and you're taking the log of that, and that means add the two logs together. So remembering that pH is simply the negative log of the hydronium, and remembering that the negative log of the Ka is the pKa, plugging those definitions in gives us this right here, and that's exactly the Henderson-Hasselbalch equation. So it's really not that difficult of a derivation, but there it is for you math types if you want that information. So let's do this example. What's the pH of a buffer that's 0.05 molar some weak acid and 0.150 molar sodium salt that weak acid? If I know that the Ka is this much, let's use the Henderson-Hasselbalch on this. Okay? So let's use that. Let's see. pH is pKa plus the log of the anion form over the acid form. I got the Ka of 6.5 times 10 to the minus 5. The pKa is, take the negative log of that. Put that value for me. Negative log, what is it? 4.19. Okay. There's nothing on the other side of the 9. It's going to cause it to round up. Okay, awesome. Okay, so 4.19 plus the log of the Which one of those is the anion's concentration? 0.05 is a 0.15. 0.15. So the other one must be, so this is going to be 4.19 plus the log of 3. Log of 3, I need a calculator able to do that. Probably a negative number, is it? So what's the final pH over the positive number? Okay, cool. So what's the, let's make it step up. Final pH is how much? 4.6. 4.66. Okay. I guess the log of 3 is a positive number. Okay. 4.66. Yay. Is the X is small, okay? How do you check if X is small? We never even got a value for X. Oh, but wait, what is the value for X? So the pH is 4.66. What is the value for X? And to the negative 4.66. Oh, what? You off? Yes. Whoa. Not the K. Oh, in my view, right. So for me, I look at Ka. Ka is 10 to the minus 5. Starting concentration is 10 to the minus 2. That's a difference of 10 to the third, which is borderline. Usually you're all right for 10 to the third. 10 to the fourth, I'm much more confident about. 10 to the third is could go either way on. Push 5%. I'm still usually going to say 10 to the third is okay. But yeah, so 10 to the fifth. And this is 10 to the minus 2. So that's 1,000 close difference. Usually okay with that. But if you want to truly find and do the X is small thing, then what you need to do, so 4.66, that's what we found, is to undo the 4.66. So the hydrogen's X is actually 2.2 times 10 to the minus 5. 2.2 times 10 to the minus 5 divided by 10 to the minus 2. Yes, under 5. 3 powers of 10 is usually enough. So yeah, Henderson-Hasselbalch is perfectly fine to do. So here's that same one that you worked on ago with the ice diagram. Okay? Just real quick, like, run it again, this time using Henderson-Hasselbalch. And it shows you the Y, the value of having the pKa right in front. It's a lot better. It's a lot more valuable piece of information as the pKa. Should get the same number you got all ago. And it should have so pH is equal to 3.15 plus the log of 0.071 divided by 0.14. So it's approximately the log of 0.5 something. Same value? You know how you round it? 2.85, 2.86, those are the same number. 2.9, that's the same value, the same again, right around it. The Ka comes back to the button, or is that pKa that you reject? X value is actually 1.4 times 10 minus 3. So yes, same as it was long ago. 4.5%. That's the initial concentration of the wheat gas. You could then divide by the initial concentration of the constant base. Why you divide it by the initial concentration? Because if you're using the extra small check, that's always been the way to check extra small. We've always checked it by seeing what hydrogen is and divided by the initial concentration. Technically, it's a gas. Although this is the first time we've had a mixture of gas and earlier, we only had one species. Every time we looked at equilibrium, we had one starting concentration. So there was only one to divide by. So, do I use my full analysis? In other words, do I use the ice diagram, initial change, equilibrium, or do I use the Henderson-Hopper law? Well, if X is small works, then usually the Henderson-Hopper law is much quicker, shorter route to the desired result. Of course, if X is small, it makes my full equilibrium analysis, it makes my ice diagram a lot simpler. You just have to make a personal choice for which one is faster and quicker for you. For me personally, I like this possible. That's what I'm going for. And for most problems, those are going to be the conditions. You're going to be under the kinds of conditions where you've got a Ka significantly smaller than starting concentration. Typical starting concentrations are going to be between 0.1 and 1. 0.5, common, 0.3, 0.2, 0.1, common. There's mine, right? There's that 10 to the third that I told you about. That's a 3. There's 10 to the third. 1,000-fold difference. 10 to the second, yeah, sometimes with 2 times. So, pH of a buffer. If you have equal amounts, then the pH of that buffer is going to be whatever the pKa is. Plug it into your Henderson-Hopper law equation, and you'll see that the log of 1 is 0. The same numbers on the top as is on the bottom, and you have the log of 1. pH is equal to pKa plus the log of 1, and you should know that the log of 1 is 0. Convince yourself of putting it in your calculator. Which means pH is equal to pKa. But if it's not, then here's some lost boxes. Nice quick resolution of that. But that's what a buffer is supposed to do. It's got a particular pH, and it's supposed to maintain. It's supposed to resist changes in pH when you add some acid or some base. The pH still changes, but it doesn't change. as much if you do not have buffer as having the buffer. If I want to actually know what the new pH will be, there's a couple of things I have to keep in mind. The first thing is there's a stoichiometry. In your lab that we did before we went off on break, in that table in the latter part where you had a fraction 1/4 and then that fraction 2/3, that 1 and the 4 actually comes from a stoichiometry calculation. I had 0.05 molar hydrochloric acid and 0.01 molar sodium hydroxide. And so when I put in 1 drop of the 0.01 molar, it would neutralize 0.01 of the hydrochloric and leave 0.04 unchanged. Second drop would neutralize 0.02 and leave 0.03 unchanged. That's 2 to 3, a 1 to 4, a 3 to 2, a 4 to 1 ratio. That's where those fractions are coming from. That is actually a stoichiometry calculation. And so, when you start adding acid or base, then the first thing you have to do is do some stoichiometry calculation to see what the new concentrations of acid and base are. When you add acid, it reacts with the conjugate base and reduces its quantity, but it increases the amount of the weak acid. When you add an acid, when you add a base, it reacts with the weak acid and increases the conjugate base quantity. But you can plug those new values into a Henderson-Hasselbalch equation. But first, you've got to do the stoichiometry to know what those new values are. You know what the originals are. Now you've got new values. Once you've done that, though, then they plug right into an equilibrium calculation. Either use an ice diagram, if that's what you're more comfortable with, or use the Henderson-Hasselbalch equation. Your stoichiometry is going to tell you what the new values of weak acid and conjugate base are. And based on those new values, you can run a pH calculation and see what the pH is. So, when you add acid or base to a buffer, the new pH is a result of a new calculation. First of all, the first thing you have to do is a stoichiometry. Alright. So here's the question. What's the pH of a buffer? It's 0.1 molar acetic 0.1 molar sodium acetate. And we have added to it 0.01 moles of sodium hydroxide. Now, first thing that I need you to recognize is that that capital M, you don't see it here, but you've seen it all along. That capital M is a molarity. That is mole per liter. So the first thing we've done in this example calculation is break that apart into its two parts. It means if I have a 0.100 molar, I have 0.001 moles in a 1 liter volume. So volume is now going to match. Now the first thing I need to recognize. If that had been 25 milliliters, then that would complicate things a little bit. But I've made life simple. I've taken 1 liter as a volume so that a 0.1 molar has within it 0.1 moles of the weak acid. And a 0.1 molar sodium acetate has 0.1 moles of acetate per liter. Okay. Alright. So it's one of the things I need to recognize. Now back to what we need to do. First thing we need to do is do some story count. There's my equilibrium. Technically this is not an equilibrium. Technically this is a one-sided reaction because this is a strong base. Just like the equilibrium of a strong acid is a large K, the equilibrium of a strong base is a large K. It means it's all pushed to the product side. So I really shouldn't be using an equilibrium arrow here. I should be using an arrow that pushes to the right. But this is what I'm doing. This is my stoichiometry. So there's my chemical reaction. It's really not an equilibrium, it's a stoichiometry. And I'm following this pattern because it's what it looks like. This looks terribly like an ice diagram. It is not. Although, it does have initial, change, and after. So maybe this is a Pickett diagram. I don't know. We don't call it that. Okay? But this is how much I had at the beginning. This second row is how much the change is. But this last one is not equilibrium because this is not an equilibrium. This is after. So this is my stoichiometry. So this is what I'm doing, stoichiometry. So please understand this is not your typical ice diagram. There is no K involved yet. I'm not using anything. But I am using a table because sometimes things are laid out more readily in a table form. These are not polarities, these are moles. This stoichiometry table must always be moles. Must always be moles because that's what stoichiometry is based on. So this is, because I chose 1 liter of solution, this is 0.1 moles of weak acid, 0.1 moles of weak base, conjugate base. And then hydroxide. And the layout here will also be a reminder to you that this is not equilibrium, this is not an ice diagram. If this was an ice diagram, you would have things lined up with that equilibrium. Right, so let's do the stoichiometry. I'm going to step in here and I'm going to add 0.01 moles of sodium hydroxide. That's how much I am. What that 0.01 moles is going to do is it's going to react. It's going to be totally consumed. And after this reaction is finished, there will be none of it left. First thing you must recognize. That hydroxide is going to get consumed and there will be none of it left. Strong base, it's going to react. Now to the stoichiometry. That 0.01 moles of hydroxide is going to react with the acid and consume some of that acid. And because the stoichiometry is 1:1, 0.01 moles is going to consume 0.01 moles of that weak acid. So I ask you, if I start with 0.100 and I consume 0.01, how much do I have left? Okay, 0.09, and if you keep track of the figures, it's 0.090. That making sense? Okay. What that's going to do is when it reacts with this weak acid, it's going to change that same amount into conjugate base. It's going to change that same amount into the conjugate base. And so those 0.01 moles of hydroxide that react with and consume 0.01 moles of weak acid are also going to produce 0.01 moles of the conjugate base. So count number 1. So that means there's going to be more of this than there was before. There's going to be more of this than there was before. How much more? 0.01 moles more. So if it was 0.100, how much is it now? 0.11. And again, keeping track of increasing figures, it's 0.110. So after the stoichiometry is all said and done, let me erase a bunch of this stuff. Then I will have 0.090 moles of weak acid left, and I will now have 0.110 moles of conjugate base produced from this stoichiometry, because all of the hydroxide is going to get used up because it's a strong base. Now that I have my new values, I can plug those into my Henderson-Hasselbalch and complete my calculation. So pH is pKa plus the log of the anion, which is 0.110, over the acid, 0.090. And the pKa, I believe, was 4.74. For acetic acid. So what's pH going to be? .83. 6 knots. I just used, I just used the Henderson-Hasselbalch. And the entire premise of the Henderson-Hasselbalch is based on X minus 1. So yeah, technically you should check. I'm a non-wanna, but technically you should. So what we just did is we did this diagram, and again, I really should get it. I really should show that as an arrow, not as an equilibrium, because that's not an equilibrium. That's a chemical reaction. That's stoichiometry of a strong base reacting with a weak acid. It's going to do its business. But those are the values I just got. Where do they come from? They come from the fact that hydroxide is going to consume some of the weak acid, making it less, but it's going to change it into the conjugate base, making it more. And then I'm going to plug that into Henderson-Hasselbalch. And when I plug that into Henderson-Hasselbalch equation, then I'm going to have my results. Now, notice there's a new line at the bottom of this. And because in my example I had a liter, 0.090 moles, because these are moles, and 1 liter is 0.090 molar. If this was 25 milliliters, or 50, or 100, or 300 milliliters, I would have to come back and put that mole back into molarity. Because by definition, all of these concentrations are exactly that, concentration. Yeah. So, in other words, this would be different if that was not 1 liter. Because I really must have molarity. I really must have no liquor. But because of my choice of just leaving 1 liter volume, it made the math simple. And 0.090 moles in 1 liter is 0.090 moles. Because technically in equilibrium, these values must be molarities, it must be concentration. So now that I've got them, I plug them into my Henderson-Hasselbalch. I go back to my equilibrium, okay, and I'm ready to go. If you like the ice diagram, use the ice diagram. That's perfectly fine. It'll work. Check your X is small, make that assumption, simplify your math, do the calculation, and get a result. What did we say a while ago? 4.66? Definitely valid. Oh, sorry, 4.3, not 4.2. See how you got. And again, if you like an ice diagram, then use an ice diagram. For me personally, I'm going for the Henderson-Hasselbalch version. Because, in my opinion, it's a much simpler choice. Now, I do have to change the K into a pKa, so that adds one step to it. But for my own personal use, that one extra step is worth it because of the result of it. Much quicker, simpler, that's how I do my result. But notice this is a two-step process. This is first, do the stoichiometry to see what the new concentrations of weak acid in its conjugate base might be. Which means I must find the number of moles. So again, if this was 200 milliliters, this would not be 0.100 moles. This would be some other value. This number of moles depends on the volume as well as the concentration. Make sure you're doing with moles. Because you're not always going to be able to do with 1 liter. But realize that the first thing is stoichiometry, and the first thing stoichiometry requires you to know the number of moles. And that's where it has to start. And once I have the number of moles, when I finish my stoichiometry, I have to put it back into molarity. And I come back to molarity to do Henderson-Hasselbalch. So first go out of molarity into moles, do stoichiometry, get those moles, go back into molarity, and work from there. Alright, we're going to stop right there for today. These next several slides. When we come back, what I want to do is look at what that same amount of sodium hydroxide will do to absolutely pure water versus the buffer that we have. Show you that buffers do indeed resist changes in pH. So our buffer went from 4.74 to 4.83. It did change. It went up by 0.09. So when we come back on Wednesday, we'll pick up here.